Here we're going to talk about reaction mechanisms, basically to talk about how we get from one place to another, the reactants to the products. So let's consider a very simple chemical reaction going from the Jackson Coffee Company in downtown Jackson to Jackson College here south of Jackson. Now here are three possible routes that I could take to go from my reactant to my product. The reaction mechanism is basically how do you get from there to there. So here are three possible routes, and there's actually an infinite number of possible routes to get from Jackson Coffee Company down to the college, because we could go, from here and then go over to Ann Arbor and then through Detroit and then way back over through to Chicago and then eventually get back here. Some of them are silly and obviously probably don't happen, but there's an infinite number of possible ways of getting there. And every set of directions, here are three of obviously infinite, is what I'm going to call a potential reaction mechanism. It's basically how the route that I got there. So in chemical reactions, when we're actually doing chemical reactions, we can't necessarily follow the molecule going from hither to yon. We have to sort of make predictions as to how we think it gets there. But what we can do sometimes is, instead of, since you can't follow me driving there, but you might be able to put somebody on a particular corner, so say right here in this corner of this intersection, put up some sort of indication that if my car flies by there, it you know it. You can't follow me, but you know that my car went by there at some point during the process. So if I have an indicator that only gives a flag or a positive indication if I pass by here, then that lends some credibility to this particular route that I actually might have gone through here because at one point I went through here. So it doesn't necessarily prove that this is the route, because of course I could come down and go way over here and still go through this little point by some other mechanism, but it gives us a little bit of indication as to what the actual mechanism is. So you can never prove a mechanism, but you can disprove a mechanism. You can never prove that this is the actual mechanism. Sorry, that's why they're always potential, but you can disprove them. So let us consider photosynthesis. So we know that we have this reaction, carbon dioxide and water react with a little bit of light to form sugar molecules and oxygen. So we know that reactions do not actually, the actual reaction, this is sort of our overall reaction. We know that this doesn't happen in one step, because remember, we think about kinetic molecular theory that the molecules actually have to bang into each other with the right orientation, and at no point are 6 carbon dioxide molecules and 6 water molecules all going to hit each other at just the right orientation with a thing of light and then all come together and form one sugar molecule. That's just unreasonable. So this is the overall reaction, basically where we started from and where we finish. But there's a whole bunch of intermediate reactions that take place that give us this overall reaction. And those intermediate steps are referred to as elementary steps. So let us consider a particular reaction where we know at the beginning of our reaction we have A plus B goes to C. A plus B goes to C. So it could take place in two different methods. I can come up with two very simple mechanisms that could explain how it's actually happening. It could be what we call a bimolecular reaction, where the two molecules A and B actually come together and stick together and form C. Or there could be some other reaction mechanism where A in fact does not react with B. A decomposes into some compound X, and then compound X, which would be an intermediate itself, it's the product of an intermediate step or an elementary step, then that X reacts with B to form C. This is also a possible mechanism because we add them up. We add up the overall reaction here is the reaction that we see, A plus B going to C. But in this case we actually have it's taking place in two steps, and it stops at this intermediate. Now to prove or disprove, we might be able to run this reaction and have some other compound that in the system that we know would preferentially react with X and turn into something else, and that if we ran that, and we might be able to come up with some secondary reaction that tells us if X ever exists in that system. And if we run the reaction and we never see any sort of indication of X ever being there, that would lead us to disprove that this is the reaction mechanism. If we have no proof that X is ever there for any period of time, then this is not the reaction mechanism. But that does not prove that this is the reaction mechanism, because we can come up with a whole bunch of different ones, right? So I put or question mark, meaning, again, we can come up with theoretically an infinite number of reaction mechanisms. So these elementary steps have a sort of like certain set of properties. We know that they must add to give the overall reaction. We will refer to reactions where we have a single molecule sort of dissociating. We call that a unimolecular reaction, so one molecule. Two molecules coming together is called a bimolecular reaction, and then of course we have trimolecular reactions. And that's about it, because we're not going to talk about quad molecular reactions, because for a quad molecular reaction that means we'd have to have four molecules all hitting each other in the right orientation at the same time with enough activation energy, which is pretty much never going to happen. The products of those elementary steps, as we said, is referred to as an intermediate. And then whatever is the slow step, the slowest step of the reaction mechanism, is referred to the rate determining step. So let us consider a reaction mechanism for a very simple reaction. So wrapped candy goes to eaten candy. Now, before we can go from wrapped candy to unwrapped candy, or to eaten candy, we have to unwrap it. So I'm going to propose a two-step reaction mechanism where the wrapped candy turns into unwrapped candy, and then unwrapped candy turns into eaten candy. And so in this case, unwrapped candy is our intermediate. Now, this first step is actually the slow step, right? So if we think of this reaction, the first step, how long it takes to sort of like unwrap the candy and get the unwrapped, think of a Hershey's Kiss. Going from wrapped candy to unwrapped candy, that takes much longer, if you will. So it's the slow step in comparison to the second step, because once you have the unwrapped Hershey's Kiss, eating that unwrapped Hershey's Kiss is very, very quick. It's the unwrapping it that goes much, much slower. So this is our two-step reaction mechanism, and we can talk about, we talk about the relative rates, and this is actually how we use it. We just sort of refer to it as slow and fast. So the reason why this is important is because when we are talking about how fast an overall reaction takes place, we are concerning ourselves with the slow step of our reaction mechanism. So what if I were to double the rate at which I was unwrapping candy? So instead of me unwrapping candy, I had me and my friend unwrapping candy. What do you think would happen to the overall rate of reaction of the eating of the candy? Again, this is our overall reaction. So if we doubled our concentration of unwrappers, this overall reaction would in fact double, which makes sense because this is the rate determining step. So however fast this is going dictates how fast this is going. Let me say that again. However fast the slow step is going is how fast the overall reaction is going. If we think about the second reaction in our mechanism, unwrapped candy going to eaten candy, if I were to somehow make this one go twice as fast, so maybe have twice as many people eating the candy, but still have, I have two people eating unwrapped candy and only one person unwrapping it, the overall reaction will not change, right? Because I have more people eating, but that's the fast step. So if I double the concentration of how many people I have unwrapping candy to make eaten candy, that's not going to change the overall reaction rate. So again, the slow step is however fast the slow step is going, is how fast the overall reaction is going. So normally we can't predict the overall order of reactions, but we can predict the orders of reaction for elementary steps via kinetic molecular theory. Again, thinking about how fast a reaction is taking place based on those individual collisions. So if we have some substance A going to a product with no intermediate, then the rate would just be first order in A, because if we double the concentration of steps in an elementary step, if we double the concentration of A, then we have essentially twice as sort of many collisions, if you will. If we have an elementary step that's A plus B goes to product, then we can predict that the order of reaction is first order in A and first order B, because if this is the actual mechanism, again, this is an elementary step, that's our prediction, that's happening in one step. If I double the concentration of A, that means I'm going to have twice as many collisions between A's and B's, so our rate will double. Same with B. So let's look at this problem quick and see that we have a reaction profile where we have our reactant A going to B. It goes through one transition state here. This is our one transition state. Here is our one intermediate. And so we have an energy of activation, which would be, first energy of activation would be from here to here. The difference between there and there is our energy of activation for the first reaction. Our energy of activation for our second reaction is from here, from essentially this point to this point. And so the energy of activation for the first reaction is higher than that of the second reaction. So that means our second step, so going from here to there, would be the faster one because it is a lower E-sub-A. We have more compounds that have that particular reactant, or more molecules with enough energy of activation. And we know that A going to B, the net energy result is a release of energy. So the overall reaction A to B would be exothermic. And of course, there's lots of possible mechanisms for this particular reaction. And so the last thing we want to talk about is what are called catalysts. So a catalyst is a substance that makes the reaction go faster by giving the reaction a different reaction mechanism. So decomposition of hydrogen peroxide to water and oxygen goes relatively slow, but if we add iodine, the reaction goes much faster. And the proposed reaction mechanism for this particular reaction is the hydrogen peroxide reacts with the iodine, forms this OI intermediate, and then that OI intermediate reacts with the other hydrogen peroxide to form water and oxygen. Now you notice the iodine started as a reactant, started and ended as a product. This is the definition of a catalyst. It's not in the overall reaction. It's not in the overall reaction, but we start with it and we end with it. It's like how much faster can I build a log cabin if I'm given a set of instructions when I start? I'll go much faster because, I have a different mechanism because I'm actually going to be following these instructions, and I'll go much more efficiently. I have the set of instructions at the beginning, I have the set of instructions at the end. The set of instructions themselves are not consumed in the reaction. So here we have iodine as a reactant in the in an early reaction, and a product in the final reaction. And then we have OI, which is a product of an early reaction, and a reactant, and a farther one, which again is our definition of an intermediate. Put one more way about what a catalyzed reaction does is catalysts do not decrease the energy of activation, because remember, adding a catalyst almost always makes the reaction go faster. We're not making it go faster by decreasing the energy of activation or changing the temperature or anything like that. What we're doing is we're offering a different mechanism that has a lower energy of activation. So here's the reaction with hydrogen peroxide and bromine turning into hydrogen peroxide. So here's that same catalyzed reaction. So uncatalyzed, without the bromine, we have to go all the way up over this peak. So our energy of activation is relatively high. But with the catalyzed reaction, we get that two-step reaction mechanism where the hydrogen peroxide reacts with bromine, and then we have that second one, but both these, we now have a two-step mechanism that has each energy of activation is much smaller than the original one, so following this reaction pathway, the reaction will go much faster. Good luck.